Hello everyone, I'm Seunghoon from Korea University. Now I present our paper called CENTRIS, a precise and scalable approach for identifying open source software reuse. This study was co-worked with Sunghan Park, Seulbae Kim, Heejo and Hakjoo. The goal of this paper is identifying open source software components in the target software. These days, open source software is reused extensively in software development. Unfortunately, reusing OSS without proper management can cause several security issues, such as vulnerability propagation, license violation, or supply chain attacks. Therefore, identifying reused components and continuously managing them is very important. However, previous approaches cannot precisely identify OSS components, mainly due to the following two reasons. The first one is modified OSS reuse, which is the cause of first negatives in component identification, and the second one is nested OSS components, which is the cause of first positives. Developers often reused a part of an OSS or changed the original structure and source code when reusing an OSS. For example, the Linux kernel reused only 5 source files from glib library with code modifications. If only a part of the OSS codebase is reused, the code similarity between the OSS and the software is very small. For this reason, simple threshold-based approaches have failed to identify many correct reused components. And the second challenge is nested components. For example, both PHP and MongoDB reuse PCRE library. In this case, there is a common code part between PHP and MongoDB due to the PCRE's codebase. Obviously, MongoDB does not reuse the entire PHP, but it only reuses PCRE in this case. However, most existing software composition analysis approaches misinterpreted that MongoDB reuses the entire PHP or vice versa. In other words, existing approaches yield many false positives due to the nested components. To overcome these challenges, we present CENTRIS, which is the first approach to precisely and scalably identify modified OSS components. Specifically, CENTRIS utilizes two main key techniques, the redundancy elimination and the code segmentation. Let me explain one by one. For scalability, we try to remove unnecessary comparisons using redundancy elimination. Note that the entire source code of an OSS is not dually developed each time the OSS is updated. For example, in this case, the function k is not changed during updates and survived up to version 3. If we naively generate OSS signature, the function k will be contained more than 3 versions. Therefore, when we compare the target software and this OSS signature, the function k will be compared more than 3 times. This unnecessary comparison hinders the scalability and the speed of matching during component identification. Therefore, we decided to store redundant functions only once in the OSS signature. Note that we store the hash value of the function source code and also record the versions that each function belongs to, as shown in the below figure. All the created signatures for every collected OSS are stored in the component DB. The next step is code segmentation. We first divide the OSS codebase into 2 parts, the application code part, indicating the unique part of the OSS, and the borrowed code part, which refers to the non-unique part of the OSS, such as reused code part. As I explained earlier, the majority of false positives are caused by nested components. We focus on the fact that all the nested components belong to the borrowed code part. Thus, we decided to remove the borrowed parts and only use the application code part of each OSS. To do this, we first select an OSS S that will be segmented and compare S with all other OSS in the component DB. Let one of them is L. We first detect common functions between S and L. Thereafter, we focus on the birth date of each common function. If a function appears in L earlier than S, it should belong to the borrowed code part of S. Thus, CENTRIS tries to detect G, which is a set of common functions that appear in L before appearing in S. We then calculate the p-value, the cardinality of G divided by the cardinality of L. If this p is greater than predefined threshold zeta value, we determine that either S reuses L or both S and L reuse some other OSS. In both cases, all functions in G belong to the borrowed code part of S. Therefore, we remove all functions in G from the function set of S to leave only the application code part of S. After repeating this process for all OSS in the component DB, we can obtain only application code parts of each OSS. Finally, we compare the target software codebase with the application code of every OSS in the component DB. If the ratio of common functions between the target software and the application code parts of S is greater than zeta, we determine that S is the component of T. More details and justifications of our techniques are explained in the paper. To evaluate CENTRIS, we collected more than 10,000 OSS projects from GitHub, which comprises a total of 80 billion lines of code. We use zeta value as 0.1, which means that we will identify a component even if only 10% of its application code was reused. To evaluate accuracy, we conducted a cross-comparison experiment using our dataset. While 95% of detected components were reused with modification, CENTRIS showed 91% precision and 94% recall in component identification. Second, even the dataset increased gradually, the elapsed time for identifying components using CENTRIS did not increase significantly, which shows the high scalability of CENTRIS. Third, we confirm that CENTRIS require less than 1 minute to identify components in the 1 million lines of code target software, which denotes the high identification speed of CENTRIS. Lastly, we compare the component identification result for 4 target software programs to that of DejaVu. Since DejaVu did not consider nested components and heavily modified components, it showed only 10% precision and 40% recall, while CENTRIS shows more than 95% precision and recall. From our experiment, we found that 95% of detected components were used with modification. However, modified components have not been properly covered by previous approaches. In this perspective, CENTRIS can be the first step towards addressing problems arising from unmanaged components, since CENTRIS can identify modified components precisely and scalably. This is the end of my presentation. Thank you for your attention. The source code and the dataset of CENTRIS are available at GitHub, and you can use the prototype of CENTRIS at iotcube.net. Thank you.
Hi, everyone. So we are live here, and welcome to the session. Our first presentation was presented by Seunghoon from Korea University in South Korea. So thank you, Seunghoon, for your interesting. I would like to know if anybody has any questions on the presentation of Seunghoon. If so, please write them in the chat. Okay, so I'm going to start with a question for Seunghoon. Okay. So in your presentation, you have validated your approach on 10,000 open source projects, which have been selected from GitHub. So I would like to know what type of projects you have selected. I mean, what kind of criteria did you use to select the data set of projects that you used for your study?
Thank you for your question. So I selected the repositories using the standard based on the GitHub stars. So I want to validate CENTRIS using some popular repositories on GitHub. So the standard is the 100 stars. So I collected repositories which have more than 100 stars on GitHub for C and C++ languages. So the Linux kernel, Redis, or TensorFlow are contained in our dataset.
Okay. So I have another question for you. How did you find these projects? How did you find that these projects related to the security issues that you mentioned at the beginning of the presentation? So at the beginning of your presentation, you illustrated like three security issues, right? Like the vulnerability propagation, license violation, and the supply chain attack. So my question is, how do you find that the projects that you have selected relate to these security issues with respect to how your approach performs?
That's a very good question. So, CENTRIS can identify the reused components with their version information. So mostly, if a vulnerability was reported to the vulnerability databases, usually the related information such as software name, the vulnerable version information are also provided. So from that perspective, if we can precisely identify the reused components with their version information, we can easily know whether the vulnerability was contained in our software or not. So when we try to find some vulnerable components within our collected dataset, we found more than 500 projects contain at least one vulnerable code in their OSS component. And also the CENTRIS can connect with the software bills of materials, which declares the components the software built with. So if we clarify the reused components and their version information, we can prevent the supply chain attacks. So from those perspectives, we think that CENTRIS can help to solve some security issues.
Okay, thank you for your answer. So we have a question from from Songjim Lee. She asks, based on your analysis, did you get any insight into the characteristics of reused components in open source software? And is there any future research plan about program synthesis or transplantation using the results of your research?
Oh, thank you for the question. So yeah, there is a very big insight in our result. So actually, we found that more than 95% of the detected components were reused with some code or structure modification. I think that point is very interesting because most of us think that developers often reuse component without modification, but actually they reused component with at least one code changes or structure changes. I think that point is very interesting, and also due to the modified reuse, previous approaches cannot precisely identify the reused component yet. So I think, yeah, also I have some future plan using our result. Actually,
you
there
want
are
to?
many.
Do you want to
Sorry.
comment? Maybe, yeah. So about the future research. Sorry if I interrupted you. Do you want to comment on maybe one of the most interesting ones? You have like about 4 minutes on that.
Yeah. So can I continue to say the
Yes,
future?
yes, yes.
Yeah. So, the next plan is we want to find some vulnerable code with some code modifications. So we found that most of the OSS components were reused with modification. And also the vulnerable code, vulnerable source code was reused with some modifications in real-world software environment. So in that point, it is very hard to detect modified vulnerable code in the software. So we will try to identify those kind of vulnerable code with some code modification.
Okay, thank you. And so Seungmi has another question. She asks, do you also check the amount of change that appeared on the reused component, like on average?
Yes, we found that most developers often reused only the half of the code base of an OSS with 5% code changes on average.
Okay. Okay, so I guess that answers also the question. Thank you for your answers. Thank you also for your interesting presentation. If anyone else has other comments, you can please just write them in the. Also, Seungmin also says thank you and compliments for your presentation. Ends here on the live chat. You can also continue into the discussion room if anybody wants to continue asking questions to our presenter, Sunghoon. You have some time in the discussion room. Whereas we will go on to the next paper, and again after the next paper is presented, you can also ask some more questions. So Sunghoon, I'd like to thank you for your answers and thank you for your time, and a special thanks also to all of the attendees. Although we cannot see you, we hope that you have enjoyed the presentation and the question and answers time. Thank you very much. Thank you again, Sunghoon.
Thank you so much. Yeah.